Okay, I'm going to torture you for just a few more minutes. All right, and this is stuff that we didn't cover today, but I wanted to get to today. So it's like it's so I can make up the lecture that I missed. Now look, three charges in a line. All right, remember forces. Coulomb's law gives us magnitude and direction of things. All right, so here's a positive charge and here's a negative charge. So they're probably attracted to each other. But what we do is we want to determine the magnitude and direction of the net force, okay, on Q1. So Q1 is being pulled this way, and it's also being pulled this way. Oh, look. Yeah, there we go. Notice a much bigger charge and smaller direction, smaller distance, so that r squared remembers in the denominator. So we've got this 0.15 squared divided, compared to the 0.2 squared. When you're dividing those, you're going to get a much larger number here. So the force is big going this way. Force is big going, the force is smaller going this way, but we just add the two forces together. It's an algebraic, it's just adding the two vectors. So you calculate the first one, Q1 and Q2, 2.7, 8.4, and then look at the picture. Okay, we found the magnitudes here. I want to make sure I'm going to show the slideshow from current slide so I can really emphasize this. Notice magnitude here, otherwise I'd have a negative here and a plus sign here. And then we're actually adding the vectors. Notice there's no arrows above these. And there you go. And you can also do it at angles. We've got bigger fish to fry. This is more for the 250 engineering types, these types of problems. I'm going to try and avoid those at all, not at all costs, but I'm going to try and avoid these types of problems. But it's the same thing with the forces on Q1. So you find F1, Q1, and now then Q2, the force on Q2 is actually, we got to break it down into its components, okay? Because it's going this way along the x direction and up this way along the y direction. Find F1 of F2, and so here's F1 on 2, F1 on 3, cross product. There's our net force, and they solve it. Okay. Now let's talk about the electric field. All right. The electric field's invisible. You can't see it. As a matter of fact, I'm going to show you something real quick. I don't know if y'all saw the movie Frankenweenie. It's a wonderful movie. It's really 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 good. This man got in the way. There's a longer one. Okay, we'll do this one. Here's Mr. Rizlewski is explaining the electric field. And he does a really good job. I think it finally got loaded. Yeah, I'm wasting your time. It's what I do. Oh, maybe if I hit play. So
lightning is simply electricity. The cloud is angry, yes, making storm. All the electrons are saying, I am leaving you. I go to the land of opportunity. The ground says, yes, we need electrons trained in science, just like you. Come, come, welcome. So both sides start to build a ladder. This man, he comes out to look at the storm. He does not see the invisible ladders. When the two ladders meet, boom! The circuit is complete. And all of the electrons rush to the land of opportunity. This man is in the way.
Okay. Anyway, there you go. That wasn't as good a clip as I showed today. I kind of got their official clip of that. But anyway, here's a little test charge. It's a really small charge compared to this positive charge here and this negative charge here. If this is a positive test charge, it will definitely be attracted to this sphere, and it'll also be attracted to this rod, so its force would probably be going this way, and it'd also be repelled by this positively charged sphere over here, and so it would feel a force this way. A negative charge, on the other hand, would go, whoa, need to get away from this guy, get away from this, get away from this guy, get away from this guy, and head towards this guy. All right? And to calculate to calculate what the electric field is at that point, then here we go. Play from the current slide real quick. Find the force per coulomb that the test charge experiences. Force per coulomb. All right, so I take the force divided by the test charge coulomb here, and I get 2.0 newtons per coulomb. And then predict the force that a charge of 12 times 10 to the 8th coulombs would experience if it replaced the test charge. Okay, so now I'm going to take a charge of 12 times 10 to the negative 8 coulombs and put it in there, and the force it would feel is, since this is force per coulomb, if I multiply now by a coulomb, I'm going to get 24 times 10 to the negative 8 newtons. In other words, the electric field is defined by the force divided by the test charge. So it's newtons per coulomb are the units for the electric field. All right, so that yields, and then there's another way. So here it is. The electric field is defined by, exists at a point, and we're doing electrostatics. We're not having things move. So force experienced by a small test charge placed at that point divided by the charge itself. So the electric field, in other words, the force in field would be that small charge times the large charge around it divided by the distance away, r squared. And so you wind up with the Q naught divides out of the force, and you wind up with the newtons per coulomb. Okay? Newtons per coulomb is the SI units for the electric field. It is the surrounding charges that create the electric field, that build the ladder. Boom! Okay? So they're building the ladder. Sorry. And we'll look at the storms and lightning, and because the Earth, remember, is positively charged, and so what happens is when lightning actually comes down to the Earth, you get a bunch of, and due to the tumultuous tumbling around inside those cumulonimbus clouds that give us thunderstorms. It's like rubbing a lot of socks, wool socks, on carpet in a dry area, and it creates a hell of a lot of charge, and the protons go up away from the Earth, and the electrons come down, and then the electrons are building their ladder of electric field coming down, and the protons of the Earth, the positively charged Earth, is building its protons coming up. Boom, there's your electric field. All right, and then if you get in the middle of that, bang, your electrons in your body, boom, you die. All right, so force equals Q naught times E. That's one equation for the force. Again, notice the electric field is by vectors, and so at this point P, if we knew the electric field EB going this way, and we knew the electric field EA going that way, now notice, positive is coming out, then F equals Q1, Q2, okay? Determine the electric field at point P. All right. Did they tell us? Yeah, we could do all that in class, but all right. The electric field does not depend on the test charge. So for a point charge Q, for just a point charge Q, the electric field is, see, look, the test charge cancels out, is equal to all the charge, I usually use a capital Q here, divided by R squared. All right, last thing, notice, the electric field caused by 2, this one, is going this way. The electric field caused by 1 is going this way. Why? Because, I want to show you this. Positive charges, the electric field comes out of, and we'll talk about, this is where we'll start on Monday. Negative charges, the electric field comes in. All right, so I wanted to write down 2 more equations for you. This is for the electric field. And remember, the electric field is a vector. We usually calculate the magnitudes and then draw the direction of it for our purposes. All right. First one, the electric field is equal to F over Q, the point charge, or you can also calculate the force. Like if you say, okay, I know the electric field and I place a charge of, 2.8 times 10 to the negative 8 coulombs inside of it. I've got an electric field of 14,000 coulombs per meter, and I put a charge of this magnitude inside there, then I could find the force on that would be Q naught times E, or QE. Okay, so there's equation 1 for an electric field. Equation 2 is equal to the electric field, the point charge is equal to K times the Q over R squared, where Q is this big glob of charge over here, where the net charge, in what I've drawn here is it's positive. This is positive Q, and then the field lines come out of it this way, and they're perpendicular to any surface that I draw around there. They're perpendicular to it. We'll talk about that later. Good job. I'll see you on Monday.